Hello, we are doing an amendment to topic 7, and here we are doing Verilog of the components we have seen. So in a way, it's a review of various constructs primarily used in sequential parts. Remember when we did the combinational parts, we put something together for the constructs of combinational, which weren't really only for combinational. Now we are doing the same thing for sequential parts. So we do the basic flip-flop. That's actually the most important. The most important is the basic flip-flop. Once you know how to do that, then you're all good to go. And we talk about synchronous controls, asynchronous control, then registers, functional registers. Functional registers is a term used for registers that do something, like a counter, like a shift register, like perhaps a register that can swap upper part with the lower part, something like this. So whatever is just beyond the limit of registering, it's functional register. I talk about output logic. If I want to put some logic on the output, how we do it, and then instantiation. So let's start with the basic flip-flop. The symbol for the flip-flop is this, and every Verilog we write is according to this notation. C1, and then I have an R, asynchronous, 1D, and then Q. Okay. I don't really need to write all the details of the inputs and outputs, but for a few of them I will do that anyway. Input, DN, clock. Usually it would be best to have the clock and reset as the first inputs. Okay, so here is the reset, here is the clock, and this is DN, and then DN. You can include the in with input since it's 1 bit, but when you go to registers, you want to make sure that you don't just put them along with clock and reset, because that has to get square brackets and the size. And here is the output, and then let's call it Q out. Okay, and then I'm calling this one Q out. Now, since the output is going to be set inside inside an always statement, I have to make it a reg Q out. Okay, Q out. All right, so that's this part of it. And then always, once you decide that this always statement is for a register, for a flip-flop, for a functional register, and what's inside it is only a register, then you will be limited with what you could put on the sensitivity list. So I say always at, okay, I decided I want a flip-flop or a register. So I say pause edge or neg edge clock. Once I do this, I call this one an always statement that is a sequential always statement. Okay, meaning an always statement for describing a sequential component. And then you put your reset. Notice that the reset is asynchronous. That's why you put it there. For the case of synchronous reset, you're not going to put it there, but I will show it to you in a second. So you say pause, edge, reset. Okay. I'll come back to this in a few minutes. Then you say, once you come inside, you say if R, or if R equal 1 tick B1, means if it's active. Active, it's Notice that I don't have a bubble here. That means this is active high. If R, then your Q out gets D in. Okay? Regarding begin and ends, if you want to put a begin here, go ahead and do it. There is an end here. Okay? Oops, I haven't done it. I'm sorry, this is wrong. If reset is 1, Q out gets 1 tick B 0. I went a little too fast on that. Then you have the else. Else is Q out gets D in. Okay, and then begin, end. So what you're saying is the flip-flop has this as the main functionality of it. So I come in here, if reset is 1, is active, Q out becomes 0. Otherwise, Q out becomes D in. That means D in gets clocked into Q out. Now, if you have other conditions, as we will be seeing, everything comes after this else. Okay? The resetting part remains intact. If I don't have any resetting, then this ends module. Let me go back to my original color. End module. Okay. If you don't have any resetting, your always becomes, so let me draw this flip-flop. And let's say this is neg edge. And this is 1D, 1D, Q, Q out, D in. This becomes always. Okay. On the neg edge, clock, okay, Q out gets D in. Okay, that's all there is to it. That's all there is to this thing over here. Of course, you have to put the module header and the end module around it as well. Okay. Something different between the combinational and the sequential parts is that when you have an always block that is sequential, you only use the non-blocking assignment. Non-blocking. For the combinational parts, you always use blocking assignments. Okay? So let me just write this down, non-blocking. Inside your always statement. And as with the always statements in the combinational parts, everything that is on the left-hand side in the always statement must be declared as reg. Once again, the part that sets the register or the flip-flop is this red thing here. The reason I'm saying this, and I keep marking this, is I'm separating the flip-flop control from the functionality of it. Okay, so when we go to the counter, then we say that, okay, all you really have to do is the else part expand upon this. Okay, and we have also have the possibility of putting a begin here. See, I can put a begin here. Let me change this. I can put a begin here and end here. And then the flip-flop functionality part becomes Q out gets D in with the begin and end. The good thing is that the red part now can be many statements, conditional statements and assignments, and assignments inside the always, not assign assignments. All right, so this is something, and I'm gonna do another flip-flop in a second, and then I'll add a few things to the output of it. Right, let me also say about this pause edge here for the reset. Say, often it's asked if reset is only level, that when it becomes 1, the flip-flops resets. So why do I have to have pause edge? See, the reason is this. When you come into the flip-flop, and let's say into the always statement, if the pause edge becomes, if reset becomes 1, if reset becomes 1, you come into the flip-flop, this catches the reset becoming 1, or ST, sorry about that. This catches the reset becoming 1, and then it just puts a 0 into Q. Okay? If I don't put the pause edge and only I put reset, what it means is if reset becomes 1 or reset becomes 0, the flow begins into this always statement anyway. If reset becomes 1, that's no problem because the if statement catches the reset and puts the 0 into Q. But what if, let's say I don't have the pause edge. If I didn't have the pause edge, reset becomes 0. That also has an activity on the sensitivity list, and therefore flow begins again. Flow begins, and then you get into this if statement. The if statement, obviously, your reset is not 1. Your reset is what? Your reset is 0. Then what happens is you go into the else part. And therefore, when reset becomes 0, erroneously, what you do, you put D in into Q out, which is bad. Okay? Which is not something that you want to do. So D in, Q out gets D in. You don't want to put D in into Q when reset becomes 0. And therefore, to avoid that, you put the pause edge here. Okay? Putting that avoids this. And therefore, you only come into this when reset becomes 1 or reset becomes active, and that if statement catches it immediately. That's for asynchronous reset. Let's do a flip-flop with asynchronous reset. I'm going to do a symbol for asynchronous reset, C1. And then I have 1 R. That means it's synchronous. The 1 on the left-hand side, on the right-hand side of the clock is used on the left-hand side of R. This is my clock. This is my reset. This is my Q. This is 1D. So the 1 that you see on the left-hand side of the R is also on the left-hand side of D. That means both of them are controlled by the clock. So let me write down the module again. Module, the flip-flop, asynchronous reset, input, D in. I decided I want to have clock and reset first. Input, D in, and the output, Q out. Output, reg, Q out. Okay, this is reg. Okay. And just write down an always statement, always on the pause edge of clock, and that's all there is to it. You don't put the reset because reset is not asynchronous, reset does not allow flow into this always statement to begin. And then you say, but then you come in and you find that your reset is active, then your Q out becomes 1 tick B 0 or simply 0. Then you have the else, and following the else you have the assignment to your Q. You say else Q out gets D in. Put a semicolon here, and oh, you don't, well, I can put a begin end if you want. You don't really have to do that. And then you say end module. All right. If you want, you can put a begin end here also. Okay. For now, I just put it there. But then, if you remove it, remove it. Let's say that I like to add a control here, and this one for enable control. Okay, so I have another input called clock enable, and this is en, and that is controlling the clock. en2 to clock. What it means is that for the thing to get clocked, you have to have the enable active. Okay? And remember that so far the bulk of the flip-flop operation is this. Okay? So it means that after the control, after the resetting, after all that, then you have you have formed proper conditions for putting D into Q out. Okay, but now I'm adding another condition, which is no, if the reset is there, reset it. But then if the reset is not there, then look to see if clock enable is 1. Only then do this red thing here. And therefore, what I do is after the else, I put if. Okay, to make it fit in this area. Oh, sorry, I had to use dark red to correspond to that thing, or brown. If enable, then Q out gets that. You don't really need the end, and this is it. Okay. If you wanted to use the else part, you could do that. You could say else, then you have to say Q out gets Q out. You don't have to. Okay, so this is not needed, because if enable is not 1, you don't do D in into Q out anyway. And so what if, when you say you don't do it, it means that you retain the old value, which is fine. All right, so this is the flip-flop here. Let's do another flip-flop. And that one, what I like to do is active low reset maybe. Okay, let's do that. Let's do a flip-flop with active low reset. C1 again. Let's do synchronous active low reset, and therefore I have one R here, and then this is Q, this is Q out, and then 1D here. Okay, and so let's write this down. Module D flip-flop asynchronous low reset, just making up names. Input, the inputs are clock and reset, and input is DN, output, it has to be reg q out, always. Once again, since it's synchronous, I just do pause edge clock. That's it. Then let's not put the begin there, and then I say if tilde reset. That means if reset is 0, reset clock dn. If reset is 0, q out gets 1 tick b0, else q out becomes d in. Okay, I'm not putting any begin and ends. Let's say that I want to add a 3-state control. Okay, now let's put the end module here. Or let's say my flip-flop has 3-state control, meaning there is this, and then there is an output enable. I'm not talking about the clock enable, I'm talking about an output enable. And this becomes my Q try, TRI for tri-state. And if I were to describe this entire flip-flop, okay, then your output wouldn't be Q out anymore. Your output would be Q try. Okay. And then you would be adding another statement here, assign. Now, since you removed your Q out from the output, you have to declare it, and you have to declare it as reg. And therefore, I now declare reg Q out. So I do have Q out now, and it is a reg, which qualifies it for receiving a value inside an always statement. And then I say Q try. That means the flip-flop is doing its own things. And then you say Q try equal. If output enable is 1, then Q out, which is really not out anymore, it's just internal, is this thing over here. Okay. Otherwise, Q try, or the actual output, becomes 1 tick B Z, or tri-state. And then you still have your end module as before. Okay, I guess I kind of swapped colors somehow. Okay, that's another flip-flop, synchronous, asynchronous, everything we have talked about, and flip-flop with tri-state, we have also talked about that. And then again, notice that the area that is the part that you put things inside the flip-flop is this over here, after you pass through all the controls and everything. And then again, you have this here, okay, after you pass through all the controls and everything else. Anything else I need to say? Well, what if somewhere you wanted to instantiate this flip-flop? Okay. If you were to instantiate it within a module, higher level module, then you say, let's call this one module higher level. Okay, and you're instantiating this flip-flop. You do D FF ALR, and then you connect your clock to the clock, your reset to the reset. I'm doing ordered connection, and then I'm doing let's say external D input. You connect it to this, so let's say this has inputs clock, reset, external D in as input, and the 1 2 3, and then you have the Q try, which maybe there is a wire here, which is Q, which is FF out. Okay, FF out. You connect that to FF out, which is the Q try is connected. This. All right. So these are some variations of flip-flops and things. All right, let's do registers, where there is really not much to registers, except that instead of 1 bit, you make it multiple bits. So let's go back to this module, reg 8, input, put the clock and reset first, and then you put your input again, this time 7:0. Okay, call it you want to call it parallel in or reg in, and then you have output reg 7:0 reg out. So everything I said in the previous slides regarding the flip-flop applies to this as well. Okay, so what you have is this is a register, and this is a register with synchronous, asynchronous, and then you have an 8-bit input, you have an 8-bit output, and that's it. Let's start with this. So you say always at pause edge clock. Let's do asynchronous as I'm showing on the right. Pause edge. Let's do neg edge. Let's put the bubble. Neg edge. Reset. Then you say if tilde reset, then your reg out gets 8 tick, 8 tick B0, else, that means if reset is not active, then reg out gets reg in. Okay, you like to put a begin and module and in module. All right. Sometime you may want to do something to the output of the flip-flop, like for example, or the register. Like here, I put tri-states on it. Maybe you are creating a an output, an extra output to tell you if the register output is 0. So what you do is, okay, let's say you have a wire. That wire may be an internal wire that you're using for something else, and let's call it 0, ZR. And if reg out is all 0, that becomes 1. So you say assign ZR equal. You can do this. You can say if reg out is 8 tick B0, then 1 tick B1, otherwise 1 tick B0. Okay? Or you can say this: nor reduction of reg out. Either one is fine. You can either do this or do this. Okay? That means all the bits of reg out. If one of them is 1, then this will be 1, but then you are NORing them together. Okay? And therefore, if one of them is 1, you get a 0, otherwise you get a 1. The key thing is here that if you have something like this, here, let me show you here. This is the NOR reduction. This is 0. Okay. The key thing is, if you have a situation like this, never ever put the 0 inside the always statement. Anytime you put something inside the always statement, automatically that inside the always statement that becomes a register. This is not a register. This is a gate that ties to the register output. Okay, the same as this 3-state structure here. The nice blue color. This one ties to the output of the register, and therefore it has to be using an assign. Never use inside a sequential always statement. Never use wires that are combinational outputs of the output. Of the register output. Let me say this. When you are writing one of these sequential blocks, the safest is to have only one left-hand side. Absolutely only one left-hand side, and that left-hand side is either your register out, direct register output, your direct counter output, direct flip-flop output, or whatever. Okay? So this is an 8-bit register, and see, I kept talking about that red area, okay? And once again, you see that after passing through the resets or enables or all that, this is the part that is the functionality of the register itself. And this is the part that changes if you have counters or registers or whatever. Okay, let's forget this. I have one blank slide, so let's do another module. Reg 8. I haven't decided what I want to put in there, but let's go to see what Verilog brings us. Reset, and let's put an output enable, and then input Okay. 7. Okay, let's say reg 8 with tri-state output. Input 7:0. D in. Output. Reg out. Reg try, let's call it. Okay. 7:0. I'm sorry. Output. Reg. That's it. 7:0. Reg try. But then I need a register, and therefore I declare here reg 7:0 Q of the register. Then I say always pause edge clock. Let's do synchronous. If reset QR gets 8 tick B0. If reset QR gets 8 tick B0, else, that means we are not resetting it. In that case, QR gets the in. But then this is only QR, hasn't gone on the tri-state output, and therefore I put an assign. And in case of assign, I say if reg try equal, if output enable is 1, then QR, otherwise 8 tick BZ. Okay, that is everything about register. Once again, you see that the part that defines my register is this. What if I have functional registers? Well, functional registers like a counter. So once again, I go inside the module, CNT down counter. Okay. Input. It has a clock. It has a reset. It has a count enable. Or let's say it's an up-down counter. Sometimes it counts up, sometimes up-down counter. Okay, so I have an up signal. If it's 1, it's it counts up. If down up. Okay, if it's 1, it counts down. If it's 0, it counts up. And load enable, which has the parallel input, and then input 7:0, pair in, output, reg, (7:0), pair out. I also have an output, carry out. Okay, do I have a carry in? I don't. That's fine. I don't have to have carry out all the time. Carry in all the time. All right, so let's do the counter. Always pause, edge, clock. Now, what I want to say here is let's not get into the resetting, asynchronous, synchronous, whatever it is already taken care of. We have already talked about the various clocking things and all that. Now what I want to emphasize is on this red part. On this red part that now we put some if statements and things like that and all that. Okay, so here is this and pause edge reset or neg edge reset depending on the clocking or depending on the enabling or the I don't have enabling here, but depending on the active low reset, active high reset and all that. So those are or synchronous or asynchronous. So those are already taken care of. Okay, and so let's assume that this is asynchronous active high reset. Then I say if my reset is active, then my pair out gets 8 tick B 0. Now here I am in the else part. That's the red part. Okay, now I can put all kinds of if statements, then statements and all that. So to make it kind of bracketed nicely, I put a begin here. So this is the bulk of my counter. All right, what does my counter do? My counter, if load is active, LD, then pair out. See, this is else. That means it's not resetting. So pair out gets pair in. Okay. If pair out gets pair, else that means load is not active. Then you want to count up or count down. Actually, if load is not active, since I don't have a carry in, since I don't have a count enabled, that means if load is not active, you either count up or count down. If you want to add a count enable, you can do that. Let me do this. Count enable. Okay, so if count enable. Okay, so you say if load is 1, you do the loading. If not, look at the count enable. Are you counting? Begin. If count enable begin. Now what I want to do, I put begin and end because it gives a nice bracketing so you don't get things confused. So here is the counting thing. And therefore, what I can do is this. Pair out gets if down up is 1, then pair out -1. Else pair out +1. Again, I don't need all these begin and ends, but it makes it look good. Okay, this is the always. This is the end always. But then my problem also requires me to do a carry out. Okay, carry out is 1 when all bits of pair out is 1. Okay, I use an assign statement for that. I intentionally put assign here to show you that it doesn't make any difference where you put it. And that becomes 1 when all bits of pair out are 1. Okay, so what I'm really showing here is this in module. What I'm showing here is that I have 2 concurrent statements. One is the always the statement within which is procedural. One is the assign statement that only takes the carry out and only takes what is the output of the always the statement and adds them together. Now that assign can be before, can be after. It doesn't make any difference. It just looks at the final output. All right, so this is the Functional registers. Functional register, instead of counting, you can shift. So let's do shifting. Okay, I'm not gonna write the module header, and I'm not gonna. Okay, let me go back here. This is the red part now. After you've gone through all the resetting and all that, this is the functionality part. Okay. If this is a shift register, right shift, left shift. So let's change this to shift register. To a shift register, a right and left shift register. Okay, right, left, shift register. Okay, what do I have? I have pair out, which is good. I can live with that. I can call the I can still have pair out, and that becomes the output. So all I'm doing is replacing this the begin part. Okay, begin. If load pair out gets pair in, else if SHEN, which is shift enable, so the inputs shift enable is added instead of the count enable. And okay, if shift enable begin, pair out gets okay, instead of down up, I have right left. It's 1 if it shifts right. So let me go back here to make sure okay. I can do something different just to show you that it can be this. If right left is 1, I'm shifting right. Pair out becomes serial in from the left, existing pair out 7:1. Okay, then I have else. That means I'm not shifting right, I'm shifting left. Pair out gets, let's say, pair out 6:0, and then serial in from the right comes there, and then begin, and then there is this end here that replaces this red circle in the counter and makes it a shift register. Also notice that I have signals. I have serial in from the left, and I have serial in from the left. I have another signal serial in from the right. I have to declare these as just inputs, and that's it. So what I'm really showing you is everything happens in the always statement. The resetting is done separately. You learn those depending on synchronization, and then the functionality becomes this. Something about the shifting, you could also use this. Okay, so if you say pair out shifted one place to the right or shifted one place to the left. The good thing about the curly brackets is that you can always do a filling. Here, the filling is always 0. So when you shift right on the left-hand side, the empty place on the left-hand side, the 0 comes in. What I'm talking about here is output logic. I guess I've already covered that, like the carry out. All I'm saying is when you have a register like this, whether it's shift register, counter, whatever it is, okay, and you want to do something to the output of it, and let's say this is reg out. You want to put some logic, you want to put some trial state. Take the always statement as is, okay, begin, and put your reg out here, conditional, unconditional, whatever, that the red part and all that. And then if you are using the reg out for some logic, always use an assign, okay? So let's say that I'm using reg out and comparing it with some 8-bit input. Okay. So make sure whatever logic, GT. Okay, assign GT equal in C, or that looks like increment, in A, input A, you're comparing it with this, you say GT if reg out is greater than in A, then GT becomes 1. Okay? What I'm saying here is if you have logic put into your output, make sure it is completely outside of the always statement, and also make sure that you never put an assign statement inside your always. That is a bad thing to do. You cannot put assign statement inside always. And once again, if I want the if I have a flag that tells me if my reg out is, let's say, negative, okay, then I say negative flag, assign, negative flag equal reg out bit number 7. Okay. So that's with the assign statements outside the always. Only put the main part of the register inside the always statement, the thing that is reg. Don't put any wires or logic that you're using outside of the register. And also I showed you 3-state logic also goes outside. And also the shift register. Remember the shift register, it has the pair in, let's say, it has the pair out, which is the shift register output, the 8 bits. And then you have an always statement with this, with that, and then an end. And here you have your pair out is set to something. Okay, now if you have serial out from the left and serial out from the right, actually serial out from the right is nothing but pair out bit 7, and serial out from the left is nothing but pair out, left is 7, right is 0. So again, don't put the SOL and SOR inside this always statement, use assign. assign serial out from the left equal pair out 7, assign serial out from the right is pair out 0. And if you like to put these assign statements for whatever reason you like to put them ahead of this, you can do that. Let's say this is shift register. All right, these are some things that I think is important to note. That was a good review, and I'm also talking about instantiation. Let's take a counter. Let's say I have module CNT8 input clock reset and count enable and input 7:0 pairing output reg, that's a counter, 7:0 pair out and module. Okay, but then you are instantiating this, and the way you are instantiating, this is the counter, this is the counter. Okay, it has a count enabled, that's it, and then it has 8 parallel in, 8 parallel out, pair in, pair out. Okay, and let's say that you have a top level module top level whatever, and there you have a let's say wire clock, where it comes from we don't really care. Let's say CK, wire CK, wire RS, and maybe some other module is providing you with an enable, so you have wire EN, and maybe the top level module has an input bus, let's say input 7:0 A bus, output 7:0 W bus, and now you want to instantiate this inside this top level module, so you do this CNT8, you're instantiating it, and that you give it an instance name, let's say C8, and then you do the port maps. Okay, you can do connection by position, or you can do connection by name. I'm going to do connection by name now. Okay, to the clock of it connects to the clock of it connects my local signal clock. To the reset of it, RST of it, see, RST is of the count, and then I'm connecting RS, which is local. To the CN of it, let's not worry about CN, okay? And to the input of it, which is dot pair in, I connect the A bus, which is local in this top level module. To the output of it, which is called pair out, I connect the W bus, which is local. What do I do with the enable of it? Okay, well, I like the count enable of it dot cen to be tied to 1. One tick be 1, which means that this is counting all the time. Okay, so this is instantiation of that component, which is really no different than the combinational components. I just wanted to do a review of that. One last thing on sequential circuits I'd like to mention. When you have a clock in your test bench, okay, everything is the same. You put values, you get times and all that, but then when you declare your clock, make sure you declare it with an initial value, and then somewhere down the line you use this always. Okay, wait, let's say 11 nanoseconds. I'm sorry, not that. Okay, always sharp sign, wait for 11 nanoseconds, and then clock becomes tilde clock. Okay, or if you want to put a limitation on the clock, this is an alternative. You can say initial, repeat 35 times. Why 35? I don't know. Wait. What is this tilde? Sorry. Sharp sign 11. Okay. Wait 13 nanoseconds. I don't know why my blue doesn't work. My blue 13 nanoseconds, and each time clock is tilde clock. Okay, the always repeats it forever. Somebody has to stop it. The initial repeats it only 35 times. And then obviously the delays are different. And make sure if you do this, your clock has to have some initial value. If it doesn't have the initial value, it has X. And then you complement the X forever and ever remains X. Nothing changes. All right, so what we have done is basic flip-flop, synchronous, asynchronous, all kinds of controls we talked about. We talked about the registers, how we expand from flip-flop to registers, the functional register counters, shift registers. Then we talk about output logic when you are putting it an output on some flip-flop, some register, some shift register. Make sure it's assigned. Don't put it inside the always statement. And always use non-blocking inside the always statement. Always use reg inside the always statement. Never put an assign inside the always statement. This is a bad thing. Okay, never put an assign inside an always. Assign doesn't go there. If the else statements go there, but not assign. Assign always outside the always statement as a concurrent statement. Then we talked about output logic, which is what I just said, and then instantiations. All right, this was supposed to be a comprehensive review of all the register or memory element description in Verilog.